Hello, today we'll be doing an APC free response from 2010. The question reads, a bowling ball of mass 6.00 kilograms is released from rest from the top of a slanted roof that is 4.0 meters long and angled at 30 degrees as shown above. The ball rolls along the roof without slipping. The rotational inertia of a sphere of mass m and radius r about its center of mass is 2/5 mr squared. Part A asks us to draw and label the forces, but not the components. So they just want the forces that are acting on the ball, on the sphere as it's going down. So it's basically like doing a free body diagram. When the sphere is right here, it has three forces acting on it. There's the normal force, which goes from the bottom straight up. That will be the normal force. There's the weight, which always goes straight down. The normal force is perpendicular to the slanted roof. And then there's friction, which opposes its motion. And that's from the bottom of the surface where the ball touches the slanted roof. So that's basically all there is to part A. Part B asks us to calculate the force due to friction. So we're looking for friction. Since this ball is sliding without slipping, it's going to have both an angular component and a linear component. So we do that, we take the equations that we know, torque is equal to rotational inertia times alpha, and we take that force, some of the forces, should equal MA, and in this case, MA is going to be, we know, mg sine theta minus friction. So at this point, we can go back here, and once we find that force, we know that this is force times radius. So the key is to find this force. We have mg, we have sine theta, and we're looking for friction. So we can do that friction is equal to mg sine theta minus ma equals friction. And now we need to find the acceleration. So I'm going to leave part B hanging right here. We need to find acceleration, and part C asks us for, part C asks to calculate the linear speed. So we're solving for velocity. Once we find velocity, we can find acceleration and go back to this equation in part B. So part B isn't done yet, but we're going to go on to C. To calculate the linear speed of the center of mass of the ball when it reaches the bottom edge of the roof. If we want to do that, we can use energy conservation. So the energy at the top of the roof is going to equal the energy at the bottom of the roof. At the top of the roof, it starts from rest, so it has purely potential. And that's going to be, for now, we'll just use the general formula. mgh equals 1/2 mv squared plus 1/2 I omega squared. And we're not going to account for any potential energy in this equation, and we're going to zero out the potential energy right at the bottom of the slanted roof, right here. So when the ball's at the bottom, it's not going to have any potential energy because that's where we're going to zero it out. So we have this formula, and we simply have to plug things in. We can just cancel out, well, we know that's 1/2 times 2/5 mr squared times omega squared. So we can cancel out the m's, and we have g. H in this case is L sine theta, as you can see. So GL sine theta is going to equal omega squared that's equal to v squared over r squared, so the r squareds will cancel. We've done that plenty of times. And so this all simplifies into 7/10 v squared. Alright, so we have this. We're looking for velocity. Now it's just simple math. We get 10/7 times 9.80 meters per second squared times the sine of 30 degrees multiplied by L, which we have is equal to 4.00 meters. So this all equals 28.00 meters per second, which equals v squared. We take the square of both sides, and we get that v is equal to 5.29 meters per second. This would have squared. So this is our velocity. We can use this velocity and go back here and use the kinematics to find acceleration. So the formula that we should be using is just a simple kinematic, right? V final squared minus V initial squared equals 2ax. Just plug in the numbers. We get that 5.29 meters per second squared equals 2 times a times x. And x in this case is going to be 4.00 meters. It's equal to the length. So we have 4.00 meters. We solve it out and we get that the acceleration is equal to 3.49 meters per second squared. And hold on, I ran out of room. We're just going to erase this part. Alright, we plug that acceleration into here. And if you do the math out, you're going to get that F is equal to 8.41 meters per second. And that's the end of part C. There's a part D. The part D is actually very simple. We can finish in like 2 seconds. Part D. I'll do it in a different color so you guys can not get jumbled up with all the other stuff. Part D simply wants to know the horizontal speed of the wagon. So W, we'll just call it velocity Wx because we're looking for the horizontal speed of the wagon. And we can simply do linear momentum. Well, yeah. Momentum is always conserved. So we have the mass of the ball, put that, and the velocity of the ball, which is what we had initially, is equal to the mass of the ball plus the mass of the wagon, which we'll just call MW. V final. And as the ball is leaving, it only has horizontal speed, so we don't need to break it down into x's and y's. We can just leave it as this, and we'll still get the velocity final, and that velocity final will be equal to the velocity of the wagon in the horizontal direction. And the reason we can use this is because the ball's going to land in there and it's going to stay there, so it's elastic. We just plug in the numbers, 6.00 kg times 5.29 meters per second equals 6.00 kg plus 12.0 kg times V final. So this is our equation. If you divide both sides by 18 kilograms, you will get that V final equals 1.76 meters per second. Hold on. Yeah, you don't really need to look at this portion. And so, though it's a little bit messy, we have successfully completed this free response. Thank you.